very much. Now this is the title Niels invented for me. Like in charge with addressing this issue. Okay, so what's the state of the art? Are based on compressible Euler equations and so-called soundproof equations, which are like derivatives of the classical compressible Busenev equations, are not recommended for weather and climate modeling. And this was thoroughly discussed in the paper Davis and colleagues 2003 in QJR. So you see, Euler is happy, smiling, and Busenev looks a little bit disturbed. So given this widely acknowledged suitability of compressible Euler equations for modeling of weather and climate, why some researchers still pursue skip it. I'm not going to start all over. So, given the possibility of compressible Euler climate, why people still pursue which are based on the Recently, in 2008, he proposed extension of his pseudo-incompressible model. Also, Arakawa and Connor, they designed hybrid system that combines hydrostatic primitive equations with anelastic or pseudo-incompressible. So there are arguments like purely mathematical, which is elegant simplicity and versatility. People just like those equations. Or they are interested in them, but there are also practical issues. The bottom line is that fully compressible Euler equations for the numerical methods for fully compressible Euler equations for low Mach number flows under gravity and taking into account all complexities of this atmosphere can be difficult. And there are some nice discussion about this in a paper by Water, Klein, and Knio in Acta Geophysica, 2011. There is a special issue. All this special issue is devoted to modeling atmospheric circulations with soundproof equations. Here I explain a little bit. This is an example of what I mean. And don't look at those three figures at once, because I just didn't know how to make them appear one after another. So let me explain what it is. This is a very simple simulation of the single one-dimensional fully compressible mode. And what we have here, this is the density perturbation normalized by the reference density, pressure perturbation normalized by reference pressure, potential temperature perturbation by reference potential temperature, and velocity perturbation because the ambient, the background state is static, divided by, normalized by speed of sound. What we have here, this is the case of small amplitude. And we simulate this thing, and you can see it behaves nicely and regular. However, after a while, if this picture would stop because it keeps repeating itself, at the end you begin to see some little evidence of nonlinearity. So this is like a small perturbation case. If we go to the amplitude here is 10% of the background atmospheric state, which is rather large. 10% perturbation is rather large, so this is on the other end. And here you can see that after the while, the waves steepen and become fully nonlinear. But still, we can get a nice solution. Now, now we go to numerical point, that for small amplitude, the solutions, numerical solutions, are not very sensitive to how you do your numerics. It's actually, you can get, this solution can be obtained with the same schema like here, but it looks as well if it free of all those special developments, shock capturing schemes, etc., etc. Just for linear, like a higher second order, like Van Roth, it will produce similar results. Now, this is the example of the same simulation like here, or calculation like here, but using this straight vanilla linear schemes. You can see that after the moment when the solution starts producing discontinuity, or basically produces whole range of scales, the numerics cannot handle this, and basically one has to go to something like this in order to get the quality solution. In itself, it's not a problem. It becomes difficult to do this if one has ambition at the same time to do this with a large time step. And this is like, for instance, the good example is in the paper I mentioned earlier. Simple example is that, for instance, if those schemes are all explicit, if I want to use the large time step and be implicit, then I have to formulate elliptic problem. And somewhere I have to give up nonlinearity in the machinery that produces those solutions. So I am back to this. This is one of those issues. Now, this is why soundproof systems offer some numerical advantages, and they offer numerical advantages beyond just the obvious one, which is ability to make calculations with the large time steps, much larger than acoustic time step. So what are those? First of all, it's a freedom of algorithmic choices. So due to the essential separability of the elliptic problem that we formulate from all other parts of calculation, it's not like in the previous example. In the previous example, in this compressible, if I want to have a implicit system, I have to make certain choices about the selection of numerical method. The good example of the same type is in those very well-known old isentropic isopycnic models. If one wants to have a rigid lid upper boundary condition, eliminate external mode, this must be done through assuring that the average mass flux is non-divergent in a mass continuity, integrated in a mass continuity equation. And this can be done, but it requires that the numerical schemes for transport of mass are linear and don't use any type of upwinding. Otherwise, there is a complication. Okay, so this freedom is very convenient. Another thing, I'm not saying that those things cannot be done in fully compressible models, but they are not that easy and it's not obvious how to do them. Maybe some people know how to do this. So another thing is that the finite volume and semi-Lagrangian compatibility of those methods. And this includes all this type of equations and methods that result from them. So this includes, for instance, that one can formulate solvers that are fully conservative, but actually one solves for primitive variables, for specific variables. I can conserve momentum, but solve for velocity. Example like this. You can do this in a fully compressible system, but it requires very special numerics, because straightforward approximation to compressible type of the equations, it requires certain way of solving those equations in order to avoid, for instance, spurious generations of buoyancy perturbations and so on. This is something that is easily avoidable in soundproof systems. And then, for instance, another aspect of this Lagrangian-Eulerian compatibility is that when one solves transport equation or transport in an element of full dynamic equations, and one wants to limit the solutions, use those like monotonic methods and so on, the limiters are based on a Lagrangian equation. So actually, limitations is of the transported specific variables, even though we solve momentum equation. This is nice, because it's physical. Then, Another thing is that soundproof systems are relatively straightforward, extend to acoustic resolving compressible model. One just replaces elliptic pressure equation with thermodynamic pressure. Basically, it's not only this, with thermodynamic pressure equation, and it's done. The other way is not that simple. If one starts with a fully compressible system and wants to design like a soundproof system, it's not that straightforward. The thing that I like the most is that this is the example that first simulation is done with an elastic system, generates like a gravity wave solution, flow past a hill, and then the model switches to fully compressible system, starting in this environment with some temperature perturbation producing like a shock waves. This is just an example. And then another aspect which is particularly nice, that soundproof systems are like portal to modeling the entire air system. Most of aspects of the air system use soundproof equations: mantle convection, ocean dynamics, then solar convection, and so on. And those are just examples of problems that we attacked with anelastic models, from microphysics through mesoscale meteorology to general circulation, from wind tunnel experiments, those experiments about ocean dynamics in laboratories, to mesoscale ocean flows, to solar magnetoconvection. And this is thanks to the properties of those equations. Numerical flexibility of soundproof equations, those all little aspects that come with it, accelerate the advancements. And actually, anelastic models were documented to work equally well on structured and unstructured meshes with static and dynamic adaptivity. This is an example from recent paper that it's a result of Christian Kuhnlein PhD thesis. It's 2012 JCP. What you see here, this is this Blossi-Durand test, when the solution goes through cycles, deforms, and then comes back. And here the mesh is changing with the solutions, but the mesh itself calculates. This is this optimization problem that I referred to yesterday. There is, in the same paper, there is another example which is like a life cycle of baroclinic eddies, baroclinic instability. And what is interesting there, that there is an entire study about how to select the criteria, the criteria for design the mesh. And one of the conclusions is that the criteria based on those indicators, based on physics or understanding the physics, win with those based on like a mechanical estimation of truncation errors. And you can take a look. I have a movie of the baroclinic instability with the self-adapting mesh, but I didn't know how to include it in the talk. So another aspect that came with our work on dynamic adaptivity is that actually the ability to work with variable geometry actually extends elasticity of anelastic systems. One of the things that anelastic equations, or generally soundproof equations, are criticized for is that they conserve the mass of the domain, that you cannot change the mass of the domain, or that you have to fix the volume. But this is the example that it doesn't have to be so. Those are two flapping boundaries. This is 3D problem, just cut through the center. There are two flapping boundaries in time, and the flow goes in, goes out, and actually the mass inside the domain changes. All of this requirement of the constant mass or volume for Boussinesq equations comes from integrability condition of the elliptic Poisson equation. And the integrability condition for the elliptic Poisson equation is imposed in Cartesian geometry. It's imposed on a velocity. It's whatever comes in has to go out. But in transform coordinates, it's imposed on a coordinates of the system we are working, or the velocity in the coordinate system we work with, this contravariate velocity minus the mesh, the velocity of the mesh. So this gives the extra degree of freedom that one can actually model with those time-dependent geometry, changing mass in anelastic systems. One thing as a digression, that another thing that defies those like established opinions is that anelastic systems were thought to be limited to small stratifications. I hope that Rupert will talk about this. There was a paper by Rupert and co-authors in 2010 that was shown that actually anelastic and pseudo-incompressible systems are formally valid for realistic stratifications. Now I want to go to applications. So 2 examples. As I said, Niels charged me with climate and weather. So there are 2 projects. One is so-called CAM-OILAC. CAM is a community atmospheric model, and OILAC is our soundproof solver. And this is the group of my colleagues, Babatunde Abiodun from Cape Town, University of Cape Town in South Africa, Bill Gutowski from Iowa State. Actually, I believe Babatunde used to be Bill's PhD student, and my long-term collaborator, Joe Prusa from Teraflux Corporation in Florida. There are some series of works related to this entire project. The project basically takes an elastic dynamical core and combines it with the physics of the community atmospheric model. And this thing has been published. There were 2 papers in 2009 on climate dynamics. And those were devoted to comparing those standard benchmarks for aquaplanet. So what I'm highlighting this with a zonal flow. Here is solution for CAM-OILAC. This is CAM finite volume version and CAM Eulerian spectral transform. And all those 2 papers are devoted to 1 to numerics, how it is done, 2nd to all those comparisons. And the results, the discussion, basically conclusion is that there is nothing indicating that anelastic equations fail to simulate like aqua planet climate. Some results are actually even better than those 2 other models. The second paper, which is from this is full-size paper in proceedings of the 5th European Conference of CFD ECOMAS in Lisbon, 2010. It's devoted to this baroclinic instability problem and comparisons with the Jablonowski and Williamson test. So the comparison is actually between an elastic non-hydrostatic results from an elastic non-hydrostatic solver and the standard hydrostatic NCAR models. And the result is that actually there is a excellent comparability of non-hydrostatic anelastic solution and primitive equation solvers for so long as there is a linear stage of development. So this goes for this is for day 6. There are some differences, and here is that the lines are from an elastic solver at resolution 1.4 degree, and the colors for primitive equation solver at the half of these resolutions. And as the time progresses, solution gets more nonlinear, differences grow. But actually, when the mesh gets refined after day 8, the refinement of the mesh improves the comparability. So basically, it's a positive outcome. The next one, this is the very recent thing, and it's paper about this in this Acta Geophysica issue. It's a simulation of West African monsoon system. It uses real topography, observes sea surface, and simulation is for 5 years. And the highlight of result, this is comparison of time latitude cross section of monthly mean rainfall, average over 10 degree west to minus 10 degree east, or 10 degree east. And what you have here, this is the average rainfall, and this is from data. Those are data. This is Global Precipitation Climatology Project, and those dashed lines are course of African East jet. So those are velocity contours, or vertical velocity contours, I believe. Next figure will explain it better. The bottom line, those are observation. This is CAM finite volume. This is CAM OILAC uniform resolution, and this is CAM OILAC with the with this adapted grid. It's a static adaptation in this case. And then the comparison, actually analysis of this indicates that this stretch grid has the best solution from all, and compares the best with the observations. And this is the vertical cross section. It shows those vertical structure. Vertical structure within those, I think color is wind in those millibars per second. And again, this is the reanalysis from ECMWF, so the observation with the observation, CAM final volume, CAM OILAC with constant uniform resolution, and stretch grid. And this one compares the best. So of course there are differences, but that nothing is perfect, but the stretch grid and anelastic solver wins. Another project touches similar, it's OILAC Cosmo development, when anelastic dynamical core is combined with a physical package of Cosmo model, European Consortium for Small Scale Modeling. And this is the team from Institute of Meteorology and Water Management in Warsaw, and this Marcin Kurowski, Zbigniew Piotrowski, Bogdan Rosa, Damian Wójcik, and Michael Ziemiański. You know some of those guys. So the idea is that the prototype Cosmo model with anelastic dynamic core based on OILAC is limited with Cosmo parametrization. This includes like a surface fluxes, moist physics, radiation, turbulence. And it has been shown to be capable of forecasting weather using raw and smooth alpine topography at least half a kilometer grid spacing. It can do better than half a kilometer grid spacing, but it hasn't been done yet. And this produces at lower resolutions, in smooth scales, in large scales, produces results comparable to the Runge-Kutta dynamical core in large scales, with more detail in a small scale. So this is what the solver does. And this is exactly what it should be. Note that this Runge-Kutta dynamical core is based on fully compressible Euler equations. And this is some highlight. So this is CAM OILAC, this is Runge-Kutta, this is at the level 1, which is like 10 meters above the surface, something like this. It's in boundary layer, surface boundary layer, and this is after 12 hours, after 24 hours, comparing with Runge-Kutta, the same thing. And when you look at the large scale aspects of the flow, the solutions are basically the same, and the differences are in detail in a boundary layer in small scales. And then this is good. So one could say, why do we need the anelastic the anelastic code if it produces similar solution? Well, the thing is that when you increase the resolution, then the Cosmo cannot handle it with the alpine topography. So this is this what I showed you before. This is now all CAM OILAC, and this is the domain has been made smaller, so this is the same simulation but at slightly smaller domain. This is 2.2 kilometer like previous one, 1.1, and this is half a kilometer. And that, again, the large-scale structure is maintained, and there is a lot of detail regarding small-scale feature. Here I'm getting to the end. So there are two remarks. This is actually my experience and probably experience of the rest of the community who pursues those codes, is that while some soundproof model may be better than others, there is not just only one. There are some different approaches to this. So while some may be better than others, it is difficult to find an example relevant to weather prediction and climate studies to show conclusively a failure of soundproof approximations. But so far, there is nothing like this. So we would like to find one and get this done. And another point is that the idea is not to dismiss those compressible Euler equations. Nobody wants to do it. But the idea is to combine the strengths of hydrostatic compressible Euler equation established in contemporary global atmospheric models and non-hydrostatic soundproof equations established in small and scale models, and to just combine the strengths of both and take the best from two worlds. And one approach and vision is to, one possibility that we see is to combine the two by using time-dependent coordinate transformations driven by large-scale hydrostatic solution, and then impose it like in the spirit of those membranes, but much more complicated, of course. So to embed an elastic equation in geometry driven by hydrostatic solutions. This is all. Thank you.
So, I mean, the way I see this is between soundproof models and compressible models, you're having to tackle the acoustic waves in one fashion. In the case of the soundproof models, you're looking at the equations and removing the acoustic modes in some sense. And in the other case, say, tackling it from a numerical perspective and using IMEX methods for compressible flow. So, but one thing that I like to, has anybody, for example, done something like using the exact same numerical methods for both inelastic and fully compressible to see the actual cost, scalability, these kinds of issues, and let's say accuracy for that matter?
Yeah, I did something like this, but it's not a comprehensive study yet. I mean, you are asking a lot. First of all, it's not easy to have the same numerics for both. There will be always some differences. And so actually, so far the comparisons are rather like, okay, one compares pseudo-incompressible with fully compressible, and then you can compare anelastic with pseudo-incompressible, and because A compares with B and B with C, then they all compare, right? This type of comparisons there are. But I also wrote a code that is, I compared some anelastic solutions with fully compressible solutions resolving acoustic modes. Then and then they have a very similar numerics. And one of the outcomes was that, for instance, for mesoscale flow past the mountains, the pressure prediction from an elastic code is basically the same like from thermodynamic pressure. I can show you this, I have. But like going through all scales, it's not done yet. And it's not easy.
What about in terms of, you're solving, in the inelastic case, you have some elliptic problem that you have to solve. That's typically?
Like the Euler solution compared to like a Runge-Kutta core is twice slower. But Euler was not optimized for, it's a factor of 2. But it's not the, I mean, Euler is twice slower than just Runge-Kutta, Cosmo Euler compared to Runge-Kutta. Cosmo is twice slower. And it's Euler was not, the second one was not so optimized, and there is an overhead for like exchanging physics. You know, if you would have instead of having Cosmo OILAC, it would be OILAC with its own physics. It would be much faster too. So it's not the, and those are quite large resolutions. Those are large systems. So there is no like a dramatic difference. There is a dramatic difference if you want to do acoustic resolving, compressible, and unelastic. Then unelastic is like 100 times faster.
We move on.
Okay.